Okay, thank you. So yes, I'm Niki Vazou, and I'm going to talk about how you can liquidate your assets or how you can do resource analysis using Liquid Haskell, which is a joint work with Martin Halley and Graham Hudon from University of Nottingham. So let me start with a simple example. I have here insert, a function that takes as input an x of type A. It takes a list x's that is sorted and puts x into the correct position in the sorted list. And the definition is here. It says if the input list is empty, I just return singleton. Otherwise, I do case analysis. If the input x is less than or equal to the head of the list, then I just put it in the front. Otherwise, I recurse. So we can use refinement types to talk about interesting properties of this function. So for example, we can talk about length preservation of insert. So here I'm using a refinement type that says that the output list O's has length that is equal to 1 plus the length of x's. And what refinement types do is basically they use SMT to automatically check such kind of properties. So if you write this down, you give it to a refinement type checker, and it says OK, which means that the length is preserved. And we have been using refinement types to reason about more interesting properties like list sortedness. But in this talk, I'm going to say how you can use this automation and refinement types to reason about resources, where in this example, by resources, I mean the number of comparisons that insert makes. Okay, so what I would like to do is I want to add something like this that says that the cost of the output computation is bounded by the length of x's. Of course, here this O doesn't exist anywhere, it's unbound. So what I will do is I'm going to use this tick data type. So I'm saying that the result of insert is a tick. I name this tick O, and then I can say that the cost to compute the result is bounded by the length of x's. And now Haskell will reject this type because my computation is not returning a tick anymore. So let's go and see what this tick is. It is a data type, polymorphic data type on A's, and it has two fields. It has a cost that is an integer, and it has an A that contains the value of the computation. So tick is an applicative. Here I am defining the two applicative operations. So it has a pure operation that says give me an x of type A, and I'm going to lift it inside a tick that has cost 0. And I'm also defining the apply operator that takes as input a function, a ticked function f, a ticked value x, and just applies this function and returns a cost that accumulates the cost of f and the cost of x. Okay, so now we have the basic mechanism to lift things inside the ticked applicative here. So if we go back to insert, we can make a program that definitely, like Haskell will accept, by just using pure to lift our computation inside the tick. So in the base case, I'm just using pure to construct a ticked list. And again, like if I want to apply ticked things, I'm using this this applicative apply operation. So this program is fine, and in fact, its cost is less than or equal to the length of x's because its cost is 0. So pure has 0 cost, and then I apply 0 and 0. Everything is 0, which is less than or equal to the length of x's. But I actually want to be able to count cost. So to do that, I am defining two more operations. They're very similar to the applicative. So I have my step operation that takes an input x and adds cost 1. And I have a variant of applicative that actually counts the application. So it applies as the applicative before, but it adds 1 to the cost. So the cost of this fancy apply is 1 plus the cost of x and the cost of f. So if we use these operations now, we can actually go and count the comparisons that we are making. So the base case makes no comparisons, pure, but in the other two cases, I'm actually making one comparison. So here I'm using step to increase my cost by 1, and here I'm using this fancy apply to again increase my cost by 1. And now again, like automatically, I can prove that the cost of all these is bounded by the length of x's, where now the cost actually count the number of comparisons that I am making. Okay, so we did insert, and let's go and use insert to define insertion sort. And insertion sort would look something like that. It will say if my list is empty, then I want to use the empty list. I use pure to lift it inside my tick. Otherwise, I am sorting my tail and bind this to inserting X on top of the sorted tail. And I want to be able to prove that my cost is bounded by square of length now. Okay, so I'm using bind, which means that actually my tick is a monad. So as in the applicative, we go and define the methods of the monad. I have return that is basically pure, zero cost. And then I have my bind operator that says give me a tick value, give me a function that returns ticks, and then my cost is equal to the cost of X. That is easy because I have the cost at my hand. But then also I am adding the cost that computation of F requires. But to get that, I need to apply F to the value of X, and then I get the cost. So this is the type. The bind has this type. But the problem is that when I am using the type, automatic SMT verification fails. So it will say I cannot prove this. And the reason is that here I am doing basically type level computations. And the SMT cannot do that because cannot do that decidable. So it will fail because it will say I cannot go and compute this, the cost of this function f. So this is a problem because we want to use these refinement types for resource analysis. So one solution that we have, it's used often in verification, is to use these ghost parameters. Okay, so what this means is I'm defining this fancy bind, and it has an extra integer argument n, and then I am going to say that the cost of the computed function is bounded by this n. So when I apply something to the function, no matter what, the cost of the computation cannot exceed n. And then here I don't have any more type level computation because I simplify all this to an upper bound that is n, that it's given like as an index to bind. And then when I apply this bounded bind, I need to explicitly say, okay, so I am binding the function that I am using. I am binded by n. In this case, n is length axis. So now my program does type check because I helped him. I helped it here, but then SMT figure everything else out. So we saw that we can do resource analysis using refinement types. And the idea is that I am using this tick monad, that I am tracking resources with step and apply functions. And the first problem that we saw is that when you're using bind, because you need these type level computations, SMT automation fails, and you need to help it. And one solution is to use this ghost parameter. Now, the other solution is to use extrinsic proofs. So intrinsic proofs are the proofs like insert and insertion sort, that all the resource information comes in the definition, in the type of the functions. And then extrinsic proofs say, okay, let the function alone with a simple bind and prove everything outside of the function definition. And here I have this example of an extrinsic theorem and proof. It says, give me as input a sorted list x's, and I am going to return a proof that the cost to sort x's is bounded by the length of x's. So I want to prove that, and I am inside liquid Haskell, so I'm defining a Haskell function that proves this property. So I am going to start from my left-hand side, and I want to come to my right-hand side of the inequality. So I have isort, I am expanding it based on the definition, and then I have bind here. So I am expanding the bind, and here I see that I have, I am sorting x's, and I am taking its value. I know that x's is already sorted because of the precondition of my function. So I'm using a theorem that says that if you sort a sorted list and you take its value, this is equal to x's. So I'm going to replace all this here with x's. And now I have my theorem, I inductively call it on smaller input. So I can use my inductive hypothesis, basically a recursive call on x's. So I know what this cost is bound to, ln of x's. And now the interesting part is that I want to compute the value of insert x into x's, which can be either 0 if my x's is empty, or 1 because my list is sorted. So I'm going to assume here that x's is not an empty list. So now I know that x's is y cons y's. And now by the definition of insert, I know that this cost is 1. And this completes my proof when I have a list with at least 2 elements. And then I have 2 base cases that Liquid Haskell will just automatically prove for me because it's just rewriting. So this is the structure of extrinsic proofs. I am defining a property, and I am proving it using Haskell. And also, like, this is cool because here, like, this theorem holds only for sorted lists. So I could not just take this and put it inside the specification of isort that is defined for all lists. Okay. The other cool thing about extrinsic proofs is that you can prove and specify arbitrary properties. So for example, in the paper, we have many relational properties. An example of this property says that sorted lists are always sorted faster than non-sorted lists. And this would look something like this. It says, give me as input a sorted list x's, give me a y's, that is a list whose length is equal to the length of x's. And then I'm going to prove that the cost of sorting x's is less than or equal to the cost of sorting y's, because x's is already sorted. And before we saw the complexity of sorting sorted lists. Okay, so in the paper we have actually encoded and proved all the properties, all the relational properties that exist in these relational refinement type lines of work that is cited here in the back, you cannot see. And we could express everything and prove it. And these systems are systems that are specifically designed to do relational cost analysis. So the proofs there are automatic. And in our case, the proofs had to be manual. But the interesting point is that just defining the tick library, we could actually express and manually prove all of these proofs. And I think that there is a nice pace of taking ideas from this relational framework and applying it in our analysis. And we can also prove other properties. So in the paper, we have many functional optimization properties. For example, this says that if I append empty with x's on the right, it's faster than appending it on the left. And so in the paper, we have developed some fancy operators that at the same time reason about resource modification and also prove that the program equivalence is preserved. So for example, this property is expressed as this refinement type that says that for any x's, empty append x's is this symbol, which means that I'm going to preserve the value but improve the cost of x's append empty. So this gives you a nice notation and a huge simplification of the proofs. And then another interesting category of our benchmarks is proving higher order properties, cost properties about higher order functions. So for example, we prove that map fusion is an optimization. And the theorem is defined with something like this that says that if I apply if I map f to x's and then map it to g, this is equal but requires length x's more steps than mapping x's to the ticked composition of f and g. And this tells you value preservation and exactly how much cost how much is the difference of the cost. And the proof of that is something like 25 lines of code. And it's a very nice, a theorem that I like. Okay. So these are some kinds of benchmarks that we tried. In the paper, there are more benchmarks. And we have benchmarks that reason about resources that it's not time, because like a cost comes from our library. And the library says that you have to step whatever you want to count. So you can step whatever you want, but there is no guarantee that what you step is what you have in mind. But there is a guarantee that the complexity, the cost that you are abstracting is whatever you stepped on. So we have a soundness property of our ticked library. And then there is this question that I cannot answer in 17 minutes, but it's a very interesting question. What about laziness? Because Haskell is a lazy language, but the thing is that the tick operations force evaluation. So the complexity that you're counting is on the forced evaluation inside the tick monad. So the time complexity that you are counting is actually eager. But if you want to count lazy complexity, what you can do is you can go and define your own lazy data types that are using tick inside the definition. And this is basically work that Daniel did at POPL 2008, and we were able to port his benchmarks and verify them using lazy ticked data types inside the tick library. So all this is in the paper, and what we saw today is that you can use refinement types, highly automated by SMT, to do resource analysis. And the key idea is that you define the tick monad that tracks the cost, and then you use refinement types to express property about this cost. The major problem that blocks automatic verification is that the bind operation has type level computation, so it breaks SMT verification, and we saw two strategies to bypass this. The first one is using ghost parameters, and the second one is use explicit extrinsic proofs. And the cool thing is that once you go extrinsic, you can express and prove everything. And with this, I want to thank you.
So we've received a few questions online, so I'll just start with one of them. Is the soundness proof with respect to some cost-aware concrete semantics of Haskell?
I don't think Haskell has concrete semantics. First, but then no, because like, let's see, the typing rules don't know about cost. Like, you are approximating the number of steps that the user is writing. So the resources that I am counting are whatever the user stepped on. It's not time complexity. Haskell doesn't know about that. Liquid Haskell doesn't know about that. It's just a library that I use to tick, to step, and then at the refinement times, I am abstracting over the steps that the user wrote, and could be time, could mean memory, could mean like number of comparisons here. Here I was not counting time, I was just counting comparison. It could be anything that the user has in mind. So no, the short answer.
So the Danielson work that you mentioned and its encoding, so Danielson is working in a call by need setting. How do you model that with ticks?
So how do you model call by need with ticks? So the idea is, for example, when you want to model lists, you say that my list data type has a head, and then it doesn't have a tail, it has a tick that once evaluated contains a tail. So to access it, I just need one step. And we use that to express all this lazy evaluation of like insertion is linear and min is also linear. But you have to modify the data types to actually trace the thunks inside the tick data type. For the sharing, Danielson's paper again has a pay thing, like a pay function, that says I'm going to pay so much. And the idea is this, like we were able to do whatever Danielson did because you do it explicit. So by default, like our library doesn't care about that, but if you are willing to like say how much you want to pay, you can encode it, and we have encoded it in our benchmarks.
Yeah.
What about sharing? So there is a function in Danielson and in our benchmarks that says go and pay so much. And this says like if you use pay, you're basically evaluating up to some point, and then you don't need to evaluate so much. But like the idea is in Danielson, and like we ported Danielson, is that once you explicitly have all this, you can use the types to reason about it.
Take maybe one of the online questions again. How can I avoid accidentally defining the wrong cost, such as your initial insert with the zero cost?
Oh, you can't. I mean, okay. So I had a short comparison with the relational resource type systems, and in this type system, or in Alex's presentation before, the cost was embedded into the typing rules. What I say here is that your type system does not know anything about the cost, so I'm just counting the number of steps. So if you want to avoid it, maybe you can use this as an intermediate language, and you like the user writes something, and then there is an automatic translation that you trust, and it inserts the steps. And this would give you some kind of guarantee. But right now, I'm just counting the steps. What is the steps? I don't know.
So that's really nice, being able to do all this with an existing tool like Liquid Haskell. If I've understood right, something that's slightly less nice about the current approach is that when I write down insert and I have the bind, I need to say at that point, okay, here's the length, rather than being able to do that later in a completely extrinsic way. Do you have any ideas about how to make things even nicer by being able to defer those sorts of steps till later?
So I believe that if you want to have type-level computations inside your type system, you may get undecidable. And the idea of Liquid Haskell is you ask to the SMT only decidable queries. So I guess if you move in another system that is okay by losing decidability, you could heuristically go and evaluate functions like this. But right now, either give explicit proofs or give cost. Like, you cannot have both decidability and type-level computations, as far as I know.
One more question online. Could you automatically translate existing functions into the cost monad using something like compiling to categories?
I think this is a nice future work. We were discussing this. I think it is in the future work in the paper. And I think it is possible, and it would be very cool if it would happen.
Any more questions from the audience? Well, then let's thank Niki again.